Welcome to the lesson on Chapter 3, Sequences and Series. What is an infinite sequence? It is a function, f, whose domain is n or n plus, that is the positive integers, not including 0. Now, very often, instead of denoting sequences by a function f, whose domain is n, and in this example I wrote the real numbers, but the range doesn't have to be the real numbers, one usually writes either the set f of 0, f of 1, and then dot dot dot, or the sequence fn, where n goes from 0 to infinity, or simply f subscript n, where n goes from 0 to infinity. And sometimes, as I said before, the domain is n plus, and therefore the sequences are defined only for n which is greater than or equal to 1. We already saw the Fibonacci sequence. This was a sequence that was defined recursively. G of 0 was 0, g of 1 was 1, and g of n plus 2 equals g of n plus 1 plus g of n. We could also define other types of sequences. For example, d of n, where dn is the nth digit of pi. So here we have d of 0 is 3, the leftmost digit, d of 1 is 1, the next digit, d of 2 is 4, the digit after that, and so on. A prefix is simply a subset of the natural numbers defined by all the i's which are less than or equal to n for some element n, some natural number n. What one could similarly consider prefixes of n plus. A finite sequence is a function whose domain is a prefix of n or n plus. And for finite sequences, we use representations such as fi, where I goes from 0 to n minus 1, or simply write them as an n-tuple, f of 0, f of 1, up to f of n minus 1. I want to define three types of sequences in this chapter: arithmetic sequences, geometric sequences, and the harmonic sequence. Let's start with arithmetic sequences. What happened to my header? There are always problems here. Don't know. Okay, so we want to talk about arithmetic sequences. The simplest arithmetic sequence is the sequence 0, 1, 2, 3, and so on, and it's defined by the identity function f of n equals n. An arithmetic sequence is specified by two parameters, a0, that's the first element in the sequence, and d, that is the difference between successive elements. For example, in the sequence defined by f of n equals n, the first element is 0, as you see over here, and the difference between two successive elements is simply 1, so d equals 1. Now, the definition of an arithmetic sequence an is as follows. It's specified by two parameters, a0, the first element, and d, the difference. And in general, the nth element, an, is defined to be a0 plus n times d. Now, the claim is that a sequence is an arithmetic sequence if and only if there exists a difference d such that for every n, the difference between an plus 1 and an equals d. Let's see how we can prove this claim. The proof is by induction. Okay? So let's start by proving that if a sequence is an arithmetic sequence, then there exists such a d such that the difference between two successive elements is always d. Okay, so we write down the definition of an because it's an arithmetic sequence. It is an equals a0 plus n times d. So we have here an equals a0 plus n times d. The same thing for an plus 1. An plus 1 is a0 plus n plus 1 times d. Now we take the difference between an plus 1 and an, and we get that the difference is d. Namely, this equality holds for every n. Therefore, we get what we wanted to prove, that there exists a d such that the difference between two successive elements is always d. Good. Now let's prove the converse direction. Assume that there is such a d, such that for every n the difference equals d. Now we want to prove that an equals a0 plus n times d. We prove this by induction on n. The induction basis for n equals 0, well, a1 minus a0 equals d. This is because of our assumption. Therefore, a1 equals a0 plus 1 times d. So we get what we wanted to prove. This is the induction basis. The induction hypothesis is that an is indeed a0 plus n times d. In the induction step, we want to prove that an plus 1 equals a0 plus n plus 1 times d. And the proof follows. The proof proceeds as follows. An plus 1 equals an plus d from our assumption. An equals a0 plus n times d. This is by the induction hypothesis. We add the d from here, and we collect the terms together, and we get what we wanted to prove. Now, an equivalent definition by recursion of an arithmetic sequence proceeds as follows. The base case for n equals 0, you just define a0 to be whatever value you want, and the reduction rule tells you that an plus 1 equals an plus d. Now, this definition is equivalent to the first definition of arithmetic sequences, and the reason these two definitions are equivalent is simply because of our claim. Notice that the definition by recursion tells us that the difference between two successive elements is exactly d. This is what we have here in the claim, and therefore the sequence is an arithmetic sequence. Conversely, if we had an arithmetic sequence, then by the claim, the difference between two successive elements is exactly d, therefore the reduction rule holds, and therefore we get that the definition by recursion is equivalent to the first definition. Okay, let's see some examples of arithmetic sequences. The first example is the example of even numbers, right? 0, 2, 4, 6, and so on. So En in general is defined to be 2 times n. Now, the sequence En is an arithmetic sequence because the difference between two successive even numbers is exactly 2. Okay, so by the claim we get that this sequence is an arithmetic sequence. Now think of the odd numbers. The odd numbers, Wn. W0 is 1, W1 is 3, W2 is 5, and so on. So in general, Wn equals 2n plus 1. Now this sequence is also an arithmetic sequence because the difference between two successive elements is 2. Okay, so we have the even numbers, the odd numbers, they're all arithmetic sequences. Now let's think of the following situation. We have an arithmetic sequence an, whose difference is d. And now we define a new sequence bn by bn equals a with index 2n. That means that we skip every second element of a in the sequence b. Now the claim is that bn is also an arithmetic sequence. Why is that? Well, the difference between bn plus 1 and bn plus 1 by definition equals a of 2n plus 2. Bn by definition equals a of 2n. And this difference, well, we're hopping over a of 2n plus 1. So this difference is d plus d, namely 2d. Okay? Good. Now, you can see that the third example is actually related to the first example. Because in the first example, what we did is we took the standard arithmetic sequence 0, 1, 2, 3, 4, 5, and we took every second element. That gave us the even numbers. And the difference in the original sequence was 1, and in the even numbers, the difference is 2. So 3 is just a generalization of the first example. Good. Let's talk about geometric sequences. Okay? The simplest example of a geometric sequence is the sequence of powers of 2. 1, 2, 4, 8, 16, and so on. In general, a geometric sequence is specified by two parameters. The first one is b0, the first element in the sequence, and the second parameter, q, is called the ratio or the quotient between successive elements. So instead of looking at differences, we're looking at ratios. So a geometric sequence bn, specified by the parameters b0 and q, is defined by Bn is defined to be B0 times q to the power of n. Good. The claim now says that Bn is a geometric sequence if and only if there exists a ratio q such that for every n, Bn plus 1 over Bn equals q. And the proof of this claim is quite similar to the proof that we had of the analogous claim in the case of arithmetic sequences. Okay, now we could define geometric sequences by recursion. How would we do that? The first element is simply b0, and Bn plus 1 equals q times Bn. And we could prove that this definition and in the first definition and the second definition are equivalent by using the claim. The claim tells us that if the ratio between every two successive elements is q, then you get a geometric sequence with ratio q, and therefore these two definitions are equivalent. Good. Let's see some examples. First example is the example of sequence of powers of 3, namely 3 to the power of 0, which equals 1, 3 to the power of 1, which equals 3, 3 to the power of 2, which equals 9, and so forth. This is a geometric sequence with a ratio 3. Now, let's consider the case where Bn is a geometric sequence with quotient q, and Cn is defined by B of 2n. Okay, so this is similar to what we did in the case of arithmetic sequences. Okay, now we claim that Cn is also a geometric sequence. Let's look at the ratio between two successive elements in Cn. Well, Cn plus 1 over Cn equals B of 2n plus 2 over B2n. Now let's divide and multiply by B of 2n plus 1. We know that the first ratio equals q. The second ratio also equals q, so we have q times q equals q squared. Namely, Cn is a geometric sequence with quotient q squared. Good. Suppose that Bn is a geometric sequence whose quotient is q, and assume that all the elements in this geometric sequence are not negative. You'll see in a second why I need this assumption. Now let's define An by An equals the log of Bn. This is where I needed that Bn be positive, otherwise the logarithm would not be well defined. Now, I'm not specifying what the base of the log is. It's not really important. You can think of it as 10 or 2 or whatever number you wish. Now, I'm taking these logs and I'm looking at An, and I claim that An is an arithmetic sequence. Why is this? Well, look at what is the log of Bn. Bn equals B0 times q to the power of n. So the log of Bn is the log of B0 times q to the power of n. The log of a product is the sum of the logs. So log of B0 I write over here, and then I take log of q to the power of n. But log of q to the power of n is n times log of q. So this would be A0, the first element in the arithmetic sequence An, and this would be my difference. The difference becomes log of q. So in An, the difference is the log of the quotient of the sequence Bn. Okay, finally, the last example. What happens if q equals 1? Well, if q equals 1, I look at Bn, which equals A0 times q to the power of n. Well, 1 to the power of n is simply 1, so Bn always equals A0, so this sequence is a very boring sequence. It's a constant sequence. Okay, good. What is the harmonic sequence? The harmonic sequence, there's only one such sequence. The harmonic sequence is defined by Cn equals 1 over n for every n. We're talking here n's which are greater than or equal to 1. We don't want to divide by 0. Okay. So the harmonic sequence is simply the sequence 1, 1/2, 1/3, 1/4, and so on. Good. Now, we're done with sequences. Let's talk about series. What is a series? A series is the sum of elements in a sequence. Okay, we're interested in the sum of the first n elements of sequences. So given a sequence AI, we're interested in sums of the form A0 plus A1 plus A2 up to AN. Okay? Good. Now, let me put back the marker. Now, let's talk about arithmetic series, okay? Let's generalize our formula for the sum of the first n plus 1 in natural numbers, sum of I from 0 to n of I. We proved that it equals 1/2 times n plus 1. This is on the chapter on induction. Now what we want to do is we want to generalize this formula. We look at a general arithmetic sequence and let Sn be the partial sum of the first n plus 1 elements in our arithmetic sequence, namely Sn equals the sum I goes from 0 to n of Ai. We want to prove that Sn equals A0 times n plus 1 plus D times n plus 1 over 2. Now let's look at this expression here on the right-hand side and compare it with the formula that we already know. Is there any similarity? Well, this part does not appear in the formula on the top, but this part does appear. Okay? So let's try to understand where this part comes from and why this D pops up. Okay? Good. Now we want to prove this theorem. There are two ways to prove the theorem. The first way is by induction. You're invited to try to prove it. I'll try to prove it by a reduction. Namely, I will assume that this equality holds, the first equality, on the sum of 0 plus 1 plus 2 up to n, and I will use this equality, or this formula, to prove the formula of the theorem. Okay? Let's do that. Good. So, we know that an is defined to be a0 plus n times d. Sn is defined to be the sum of the first n plus 1 terms of the sequence, and we want to prove that Sn equals this expression. We also know that if we look at the arithmetic progression, sum of I equals 0 to n of I, and we denote this sum by Sn hat, then Sn hat satisfies that it equals 1/2 times n plus 1. Okay, this we showed in the chapter on induction. Okay, so now we want to evaluate Sn. So Sn, by definition, is the sum of Ai. I goes from 0 to n. Now, instead of writing Ai, I write what it equals. It equals A0 plus I times D. So I write here A0 plus I times D. I look at this sum, and I say A0 is fixed. I can take it outside of the summation. How many terms do I have in this summation? I have n plus 1 terms, because I start in 0 and I end in n. So I have n plus 1 terms, all of which equal A0. What can I say about the second part, I times D? Well, D is constant, right? So I can take it outside of the summation. So here it is, D. And I'm left with the sum of I goes from 0 to n. But this part, I already know what it is. This is the famous Sn hat. Good. So now I can replace this sum by n times n plus 1 over 2. And I got what I needed to prove. Okay? Now you might ask, good, we have a closed expression for Sn. How fast does Sn grow? And the problem is that we haven't defined what it means to grow slowly or fast, and how to compare rates of growth of different functions or different sequences. We will do this later, and this will become a very interesting question. Good. Now we want to talk about geometric series. Geometric series, namely sums of elements from a geometric sequence. Okay, so let's assume that Q does not equal 1, and let Bn be B0 times Q to the power of n, and define Sn to be the sum of Bi, I goes from 0 to n. We want to prove the formula that Sn equals B0 times Q to the power of n plus 1 minus 1 divided by Q minus 1. Before we prove this theorem, let's use it. Let's consider two examples. In the first example, I'm looking at the summation of the powers of 2 from I equals 0 to n minus 1. And I claim that it equals 2 to the n minus 1. Let's see why. Well, if I look at the sequence, geometric sequence of powers of 2, then the first element is 1, because I have 2 to the power of 0, and my quotient is 2. I plug it in my equation, what do I get? B0 is 1, Q is 2, 2 minus 1 is 1. So I have here 1 divided by 1. That cancels out. It's not interesting. And I'm left with 2 to the power of, and I did my summation from 0 to n minus 1, so I had only n terms in the summation, right? Instead of n plus 1 as I have over here. So this would be 2 to the power of n minus 1. And this is what I have written here. Good. What happens if I look at the negative powers of 2? Namely, I'm looking at the geometric sequence that goes like 1/2 plus 1/4 plus 1/8 and so on. Okay. Here, the first element is 1/2, and every time the next element is smaller by the factor of 2. So my Q is 1/2 as well. Let's plug in the equation we have. B0 is 1/2. And now, instead of looking at Q to the power of n plus 1 minus 1 over Q minus 1, let's multiply both the numerator and the denominator by minus 1. So we get here 1 minus Q to the power of n plus 1 divided by 1 minus Q. Good. So 1 minus Q is 1/2. I multiply it by B0, which is 1/2. So it's dividing 1/2 by 1/2, I get a 1. I'm left with Q to the power of n plus 1 minus 1. Now in this summation, again, I have only n terms. So the exponent here is not n plus 1, but n. Therefore, I get 1 minus 1/2 to the power of n, namely 2 to the power of minus n. Okay, so we're left with the proof of the theorem. Let's try to prove it. In order to prove the theorem, let me first prove a lemma. The lemma actually proves a special case of a geometric sequence in which the B0 is 1. So I have B0 equals 1, and then I multiply by Q, and I multiply by Q again, and so on and so forth until I reach Q to the power of n. So this is what I have here in this parenthesis. This is the sum of the first n plus 1 terms of a geometric sequence in which the first term equals 1, okay, rather than B0. And my claim is that this sum times Q minus 1 equals Q to the power of n plus 1 minus 1. Now this lemma actually holds even if Q equals 1, right? Because if Q equals 1, this part equals 0, and this part equals 0, and I get 0 equals 0. Okay? How do you prove this lemma? Well, I just open the parentheses. I first multiply all the elements over here by Q. So I get Q times 1 is Q, Q times Q is Q squared, up to Q to the power of n times Q, I get Q to the power of n plus 1. Then I multiply all the elements here in the parentheses by minus 1. So I get minus 1 minus Q squared up to minus Q to the power of n. I notice that things cancel out. The Q cancels with a minus Q. The Q squared cancels out with a minus Q squared, and so on. The Q to the power of n cancels out with the minus Q to the power of n, and I'm left with the minus 1 over here and the Q to the power of n plus 1 over here, and that's exactly what I wanted to prove. Great. Now, I use this lemma in order to prove the formula for the sum of the geometric sequence, right? The geometric series, right? The only difference I have to notice now is that in the geometric sequence, the nth element is not Q to the power of n, but rather B0 times Q to the power of n. So when I look at this sum, Sn, it's B0 times 1 plus Q up to Q to the power of n. Now, for this thing, I already have an expression. It is Q to the power of n plus 1 minus 1 divided by Q minus 1. Okay? Notice that I can divide by Q minus 1 only if it's different than 0. It's not if it doesn't equal 0. And indeed, I assumed in the I assumed over here that Q does not equal 1. Therefore, I could divide by Q minus 1, and I get the formula which I wanted to prove. Good. Let's look at the harmonic series. The harmonic series is the summation of the elements from the harmonic sequence. Namely, it is 1 plus 1/2 plus 1 over 3 plus 1 over 4 up to 1 over n. Okay. Now we claim that for every k, h of 2 to the power of k is bounded by above by 1 plus k and bounded by below by 1 plus k over 2. Getting an exact expression for h of 2 to the power of k is complicated, and you always have some error term here. Here, notice that the difference between the upper bound and the lower bound is just k over 2. Okay? Now, why is this theorem interesting? It might remind you of looking at the integral of 1 over x from 1 to n, and indeed there is a similarity between these two things. The reason we're interested in it is we want to show that, first of all, h of n tends to infinity as n tends to infinity, and you get this from the lower bound because the lower bound tends to infinity as k tends to infinity. And secondly, we learn that h of 2 to the power of k does not grow too quickly. It grows as the log of the subscript. Log of 2 to the k, base 2, is k. So it's roughly log of the number of elements we're adding. Okay? Good. How do we prove this theorem? Okay. Let's prove the upper bound. We want to prove that h of 2 to the k is bounded from above by 1 plus k. How do we prove this? The proof is by induction on k. Okay? The induction basis for k equals 0 says h of 2 to the power of 0, 2 to the power of 0 is simply 1, h of 1 is simply 1, is less than or equal to 1 plus 0. So this is a trivial case. The induction hypothesis says that h of 2 to the k is less than or equal to 1 plus k. Now let's prove the induction step. Let's bound h of 2 to the power of k plus 1. Now what do we have here in h of 2 to the power of k plus 1? We take the summation of the first 2 to the k elements, and then we take the summation of the next 2 to the k elements. Namely, from I goes from 2 to the k plus 1 up to 2 to the k plus 2 to the k. Okay? And we take the summation of 1 over I in this range. Great. Now, the induction hypothesis tells us that h of 2 to the k is bounded by 1 plus k. What can we say about the summation we have over here? Well, notice that as I grows, 1 over I becomes smaller. So we're taking a range of i's between 2 to the k plus 1 and 2 to the k plus 2 to the k. Namely, 1 over I is always greater than 2 to the k. 1 over I is always less than or equal to 1 over 2 to the k. Okay? So we can take this summation with a constant in the sum, which equals 1 over 2 to the k. Now, how many times are we doing the summation? The summation goes from I equals 2 to the k plus 1 up to 2 to the k plus 2 to the k. Namely, we're doing the summation 2 to the k times. Great. So we have here 2 to the k times 1 over 2 to the k. So in total, we bounded by 1 plus k plus 2 to the k times 1 over 2 to the k. But this product, 2 to the k times 1 over 2 to the k, is 1. So we get 1 plus k plus 1 bounds h of 2 to the power of k plus 1. And this completes our proof. Thank you very much.